Let's take a look, for example, 2 at a rational function. This one's going to have asymptotes. I want to sketch the graph of this function. We're going to use the same steps we did before when sketching a graph. First step is define x-intercepts. Now we know for rational functions is where the top equals 0 and the bottom does not. So we're just going to set x squared equal to 0 and we get x equals 0. We know that if we plug 0 into the bottom we get 1, so we know that's an x-intercept. So we have one at 0, 0. That kind of already tells us what our y-intercept is for step 2. When we plug in 0 for x, we get 0, 0. So it's going to cross through the origin. Step 3, we're going to figure out our asymptotes. We know it has whenever the bottom equals 0, it's a vertical asymptote, provided that it's not the same for the top. In this case, we get x equals negative 1. Give me 1 second here. Okay, so x equals negative 1 is our vertical asymptote. For horizontal, we see that the top exponent is bigger than the bottom, so there is no horizontal asymptote. Now, what do we know though about this? If the power is 1 more bigger than the bottom, it's going to have a slant. So we're going to have to do some long division here to figure that out. So we're going to do some long division. If you need some catch up or a refresher on that, you can watch my video on dividing polynomials. At any rate, we're going to get x minus 1 at the top. So we know that our slant asymptote is y equals x minus 1. So we will sketch a dotted line there on our graph to indicate there's a slant asymptote there. Next, for step 4, we're going to figure out increasing and decreasing intervals. That involves taking the derivative. Here we have a quotient, so we'll be using the quotient rule. I will label my top a and my bottom b. A prime would be 2x, b prime would be 1. Quotient rule is a prime b minus ab prime over b squared. We're going to be plugging all of this in, a prime b minus ab prime over b squared, and simplifying. The top is going to become 2x squared plus 2x minus x squared. 2x squared minus x squared is just x squared, so the top is just x squared plus 2x. The bottom is x plus 1 squared. We've got to figure out where the derivative doesn't exist as part of our critical values, in other words, where the bottom equals 0. That's whenever x equals negative 1, the bottom will be equal to 0. We also have to figure out where the derivative equals 0, so we're going to be setting the top equal to 0. Pulling out an x, we get x equals 0 and x equals negative 2. So if I circle these, you can see we have 3 critical values. So we're going to have 4 intervals to test for increasing and decreasing. Here are our 4 intervals, negative infinity to negative 2, negative 2 to negative 1, negative 1 to 0, and 0 to infinity. Our first test value, we're going to plug in negative 3 into the derivative to figure out increasing, decreasing. We get 3/4 back. That's a positive number, so we know it's going to be increasing from negative infinity to negative 2. Again, that will help us sketch our graph. We know it's going to start out going like this. From negative 2 to negative 1, plug in negative 1.5 into the derivative. We get negative 3 back, so we know it's going to be decreasing on this interval. From negative 1 to 0, we're going to plug in negative 1/2 into our derivative. We're going to get negative 3 back, so it's going to continue to decrease from negative 1 to 0. And from 0 to infinity, we'll plug in 1 into the derivative. We get 3/4 back, so it's going to be increasing again on that interval. For step 5, we're going to put in our relative extrema column. We know that from at negative 2, it goes from increasing to decreasing, so there's a possible extrema there. That would be a possible relative max. But at negative 1, it goes from decreasing to decreasing, so no relative extrema there. From at 0, it goes from decreasing to increasing, so that's a possible relative min at x equals 0. So we'll be plugging these back into our original function to see if in fact we get a point back. So we plug in negative 2 back into the original, and we get 4 over negative 1, which is negative 4. Since it went from increasing to decreasing, that will be a relative max at negative 2, negative 4. However, when we plug in 0 back into the original, we get 0 over 0. That's also a point, but it's going to be a relative minimum because it went from decreasing to increasing. So both of those worked out. This one's the relative max, this one's the relative min. It's going to be very helpful when sketching a graph because that's going to tell us where it changes direction. Step 6, we're going to determine concavity. For concavity, you have to take the second derivative. Here's the first derivative. For the top, it's going to be x squared plus 2x. Derivative of that, a prime would be 2x plus 2. For the bottom, we will use the power rule, so it'll be 2 times x plus 1 to the first, which also ends up being 2x plus 2. It normally doesn't happen, but here we have the derivatives of top and bottom are going to be the same. Then it's going to be a prime b minus ab prime over b squared for the quotient rule. A prime b minus ab prime over b squared. We're going to simplify this out a little bit. Notice both of these have a 2x plus 2 in them. We're going to pull that out of the GCF. Okay, so we're pulling this 2x plus 2 out. We're going to be left with x plus 1 squared minus x squared plus 2x. So here's the 2x plus 2 that we pulled out. And this we will have to multiply out, as well as distribute this minus into both of these using some PEMDAS. This will become x squared plus 2x plus 1. Then we will distribute the minus into both of those. So here's what's kind of handy. This x squared is going to cancel. It's going to be 2x minus 2x. Let me show the distribution here. Those are also going to cancel. Actually, you're just going to be left with a 1 inside of all of this times 2x plus 2, which just leaves you with 2x plus 2 times 1, which is 2x plus 2. Again, this is our second derivative. We're finding it so that we can figure out where our concavity intervals are. So we can actually pull a 2 out here. We're left with 2 times x plus 1 to the first. And we have an x plus 1 to the fourth on bottom. So this is going to cancel, just become x plus 1 cubed on the bottom. And a 2 on top. So it's kind of crazy. We did a lot of simplification to get a pretty simple second derivative. Now for critical values, it's where the second derivative equals 0 or doesn't exist. Critical values for concavity. So we're just going to set the bottom equal to 0 and do some simple math, and we get one critical value, x equals -1. So only one possible place where the concavity changes. So we have two intervals, -infinity to -1 and -1 to infinity. We're going to plug in -2 to the first interval. We get -2 back. Plugging into the second derivative, that means it's going to be concave down the interval -infinity, -1. For our second interval, we're going to plug in 0. We get +2 back. So on that interval, it's going to be concave up. Next, for step 7, we're going to check for inflection points. So at this value that they share, -1, there's going to be a possible point of inflection since it went from concave down to concave up. However, when we plug x equals -1 back into the original function, it's 0 on the bottom. And so there is no point of inflection there. We would have known that already because there was actually a vertical asymptote at x equals -1. It really can't be an inflection point. Okay, so at f of -1 is undefined. Had to fix that. It said f of -2. We know it's undefined already because at x equals -1 we had a vertical asymptote. So yes, the concavity changes there, but it's not a point of inflection. It's going to be an asymptote. So that leads us to our next step, which is to plot and label our points in asymptotes. So I want to talk a little bit about each one of these. We found that there was a slant asymptote at y equals, it's been a while, so I have to refresh my memory here. Okay, so it was at y equals x minus 1. You want to make a dotted line there because it is an asymptote. And then we had an asymptote at x equals -1. We had a relative max at -2, -4, so you know it's going to go from increasing to decreasing, and a relative min at 0, 0, which also happens to be an x and y intercept. So actually, we don't really need any additional points here because We already have our asymptotes. We already know what our min and max are. We have no inflection points. We can easily just kind of connect the dots here and be done with our graph. So for step 9, we don't really need any additional points. We can easily connect these dots. Now for step 10, we do want to kind of keep in mind where this is increasing and decreasing. When it's going to be increasing from -infinity to -2, so we're going to kind of start to go up there. And it's also going to be increasing from 0 to infinity, like that. It's going to be decreasing from -2 to -1. So once we get to -2, since we know it's a relative max, we're going to kind of go like this. And then also, it's going to be decreasing from -1 to 0, going back to increasing from 0 to infinity. So at 0, we'll kind of go like this. It's going to be concave up from -1 to infinity. So from -1 to infinity, we're going to be making a U shape. Okay. When it's going to be concave down from -infinity to -1, so we're going to be making an upside down U. So we're just using that information to connect the dots. And now that we've taken all this into account, let's go ahead and sketch this graph. Okay, so we're just going to go ahead and connect these dots with all of that information. Let's take a look. So we can see it's concave down, and then a relative max at -2, -4, and then it goes to concave up from -1 to infinity with the relative min at 0, 0. Now let's just kind of take a look at everything we've got visually. It starts out concave down, and it has a relative max at -2, -4. Then it jumps at this asymptote at x equals -1 and goes to concave up with a relative min at 0, 0. And we can see that we sketched our graph around these two asymptotes at x equals -1 and at our slant asymptote y equals x minus 1. That's it for our graph, rational function graph, x squared over x plus 1. We can see that when we use all of this information together, it makes a nice complete graph. If you have any other questions about this, let me know.